In this video, we're going to learn all about the definite integral, how it represents the exact area under a curve, and walk through many examples. We'll begin by introducing the idea of a Riemann sum and walk through an example to see how it approximates the area under a curve using rectangles. Then we'll see how taking the limit of a Riemann sum leads to a formal definition of a definite integral. We'll cover the main properties of definite integrals and work through examples that include evaluating integrals using limits, interpreting them as areas, and using the comparison property to estimate their value. Be sure to download the free guided notes to follow along, highlight the formulas, and work through these examples with me. Let's start by learning what a Riemann sum is and how it's used to approximate the area under a curve. A Riemann sum is the approximation of the area under a curve, such as the curve shown here, y is equal to f of x, over a closed interval, such as the interval from a to b shown here in our graph. A Riemann sum is notated as capital R sub n, and it's the sum from I is equal to 1 to n of f of x sub I star times delta x, where delta x is equal to b minus a, that's the right endpoint minus the left endpoint, divided by n, which is the number of rectangles. X sub I star varies depending on if you're using left endpoints, midpoints, or right endpoints. In a minute, we'll walk through an example using left endpoints and using right endpoints. If f of x is greater than or equal to 0, shown in the graph up here, R sub n is the sum of the areas of the rectangles. If f of x is greater than or equal to 0 and less than or equal to 0, that just means you have a curve like the one shown down here that lies above the x-axis and below the x-axis, then R sub n is the sum of the areas of the rectangles that lie above the x-axis, such as these, minus the sums of the areas that lie below the x-axis, which is these. We're now going to walk through an example where we're going to evaluate a Riemann sum. We're going to evaluate the Riemann sum for a function f of x is equal to 2x minus 4 over the closed interval from 0 to 3 using 6 subintervals, and then taking the sample points to be right endpoints and then left endpoints. Just to make things easier, over here on the right, I've written down the formula that we need to use to evaluate these Riemann sums. I went ahead and graphed the function y is equal to f of x, which is equal to 2x minus 4. And I broke up our region into 6 subintervals. Notice that our values of x go from 0 to 3. We're going to start by calculating delta x. Our delta x is equal to b minus a all divided by n. So this is just 3 minus 0 divided by n, which is our number of intervals. And in this example, we have 6, so we're going to divide it by 6, and we get a value of 1/2. I'm going to highlight that because we're going to need that in a minute. Let's first find the Riemann sum when the sample points are right endpoints. Since we have 6 subintervals, we're going to write our Riemann sum as R sub 6, and it's equal to the sum, looking up here at the formula on the right, from I is equal to 1 to 6 of f of x sub I star times delta x. And our f of x is equal to 2x minus 4. Since we are using right endpoints to calculate the height of each rectangle, that's these points right here, we can say that x sub I star is just equal to x sub I. And the formula for that is a plus I delta x. A is our left-hand endpoint, which is 0. So we just have I times delta x, which we calculated to be 1/2. So this is I times 1/2. And now let's see what these points are. I starts at 1, so this is going to be 1/2. And then when it's 2, we get 1, and then we get 3/2. We get 4/2, which is 2, and then we get 5/2. And then our last one is when I is 6. 6 divided by 2 is 3. R sub 6 is then equal to f at our first point, so that's f at 1/2, plus f at our next point, which is 1, plus f at 3/2, plus f at 2, plus f at 5/2, plus f at 3, and then all of this is multiplied by delta x, which we already calculated to be 1/2. Now we're going to substitute in that our function f is equal to 2x minus 4. This gives us r sub 6 is equal to 2 times 1/2 minus 4, plus 2 times 1 minus 4, plus 2 times 3/2 minus 4, plus 2 times 2 minus 4. And then our next one is 2 times 5/2 minus 4, plus 2 times 3 minus 4. And then all of that is multiplied by 1/2. Now let's add all of this up. I am going to collect all of these minus 4s at the end, and we'll do our multiplication first. We have 2 times 1/2 is 1, and then we have 2 plus 3 plus 4 plus 5 plus 6. Now we're going to subtract off our 4s. There are 6 of them, so we're going to subtract 4 times 6. And then we have our 1/2. Let's see what we get. We can add these numbers first. That's going to give us 10. And then we'll add these numbers. So that's 11. So we have 10 plus 11. And then we'll subtract off 24, multiply this by 1/2. And this gives us 22 minus 24. So this is minus 2 times 1/2. And that gives us a value of minus 1. And that's what our Riemann sum is equal to when we use right endpoints. Let's now do the same type of calculation, but now we are going to use left endpoints. Our formula is going to be the same. We have r sub 6 is equal to the sum I is equal to 1 to 6, f of x sub I star, delta x, and our f of x is again 2x minus 4. Now what's changing is our x sub I star. Because we are using left endpoints, let's go back up here and I'll highlight these so you can see what they are. We're using these 6 endpoints. Our x sub I star is notated as x sub I minus 1, and this is equal to a plus I minus 1 times delta x. Again, a is 0, so this just gives us I minus 1 times our delta x, which is 1/2. The delta x doesn't change when you use left-hand endpoints versus right-hand endpoints. Let's now write down what these endpoints are. We're going to start with I is equal to 1, so that gives us 0. And then we have 1/2, 1, 3/2, 2, and 5/2. We'll squish it in there. Now let's write down what R6 is. It is going to be f at 0 plus f at 1/2 plus f at 1 plus f at 3/2. And then we have f at 2. And then lastly, we have f at 5/2. And all of this is multiplied by 1/2. Now we're going to substitute in that f of x is 2x minus 4. And we get minus 4 plus 2 times 1/2 minus 4. And then we have 2 times 1 minus 4. And then 2 times 3/2 minus 4. And then we have 2 times 2 minus 4. And then we have 2 times 5/2 minus 4. And we multiply all of this by 1/2. Now let's go ahead and let's add this up. We'll save the minus 4s for the end. So this gives us 2 times 1/2 is 1. And then we have 2 plus 3 plus 4 plus 5. And then we subtract off 4 times 6 because there's 6 of them. And we multiply that by 1/2. Let's see what this gives us. 1 plus 2 plus 3 is 6. And then if we add 4, we're going to get 10. And let's go ahead and add 5. So that's just 15. Minus 4 times 6, which is 24, times 1/2. And this is minus 9 times 1/2, which gives us an answer of minus 4.5. And that's what our Riemann sum is equal to when we use left endpoints. Notice that these two answers are very different. The reason for that is that we only used 6 subintervals. The exact answer is equal to minus 3. So you can see that the exact value is between our two answers. If we use more subintervals, then our answer is going to get a lot more accurate. We're now going to learn how a definite integral is defined as the limit of a Riemann sum, go over some properties that you'll need to know, and walk through an example. Let's begin with the definition of the definite integral. For a continuous function f of x on a closed interval from a to b, the definite integral of f from a to b is defined as the integral from a to b of f of x times dx. And this is equal to the limit as n goes to infinity of the Riemann sum I goes from 1 to n of f of x sub I times delta x. A really important thing to remember is that a definite integral equals a number. It does not equal a variable. Let's now go over the notation. This symbol is the integral sign. It is shaped like an S because integrals represent the sum of the area under a curve. A is called the lower limit of integration, and B is called the upper limit of integration. The function that we're integrating, f of x, is called the integrand, and dx is the differential. X sub I star then is any sample point chosen within the subinterval. Let's now go over 3 really important properties of definite integrals. The first property tells us that the integral from a to b of f of x dx is equal to minus the integral from b to a of f of x dx. You just have to remember, if you switch the limits of integration, you have to multiply by a negative. The second property tells us that the integral from a to a, notice that that is the same point, of f of x dx is equal to 0. The reason for this is that if you're integrating from a to a, your x value is not changing, so your delta x is equal to 0, and the area under your curve has a width of 0. The third property tells us if you have some point C between a and b, you can split up your integral. And you can write the integral from a to b of f of x dx as the integral from a to c plus the integral from c to b. Let's now walk through an example. In this example, we are given a limit, and we are going to express the limit as a definite integral on the given interval. Our limit is the limit as n goes to infinity of the Riemann sum I goes from 1 to n, x sub I star divided by x sub I star squared plus 4 times delta x. And our interval is from 2 to 5. The limit of this Riemann sum is equal to the integral from a to b of f of x dx. This function here is f of x sub I star, so to find f of x, we just get rid of the I and the star. And then over here, we can see that a is 2 and b is 5. So we can write down that this is the integral from 2 to 5 of x, all divided by x squared plus 4, and then instead of a delta x, we're going to have dx. And there's our answer. We're now going to walk through an example where we're going to evaluate a definite integral using the limit definition. This is a difficult problem, but don't worry, I'll walk you through it step by step. We're going to evaluate the definite integral using this limit definition and these formulas. The limit definition of a definite integral is the integral from a to b of f of x dx is equal to the limit as n goes to infinity of the sum I is equal to 1 to n of f of x sub I times delta x, and x sub I is a plus I delta x. The formulas that we need to use are listed in this second box. We have the sum I goes from 1 to n of a constant, and then we have the sum of I, and then I squared, and I cubed. And we'll use these in just a minute. Here's the example that we're going to do. We're going to evaluate the integral using the limit definition. The best way to begin is to start out by writing down what the limit definition is. Our integral using our limit definition is the limit n goes to infinity, the sum I goes from 1 to n of f of x sub I times delta x. And let's write down that x sub I is equal to a plus I delta x. Let's now find out what delta x is. The formula for delta x is b minus a all divided by n. If we look back at our integral, we can see that a is 1 and b is 3. So this gives us 3 minus 1 all divided by n. So this is 2 divided by n. And now we can write down what x sub I is. X sub I is then a, which is 1, plus I times delta x, which is 2 divided by n. Now we're going to substitute in f of x sub I and delta x into our limit. F of x is this function here, 2x minus x cubed. So let's go ahead and put that in. This gives us the limit as n goes to infinity. The sum, I goes from 1 to n. F of x sub I is now 2 x sub I minus x sub I cubed. And then our delta x is just 2 divided by n. Now we're going to substitute in this expression for x sub I. This gives us the limit as n goes to infinity. The sum, I goes from 1 to n, 2 times x sub I, which is 1 plus 2I over n, minus x sub I cubed, so this is minus 1 plus 2I over n cubed, and then all of this gets multiplied by 2 over n. I think what makes this problem so hard is there's just a lot of algebra to be done. Notice right here that we are going to have to cube 1 plus 2I over n. To make things easier, let me write down this formula. A plus B quantity cubed is equal to A cubed plus 3 A squared B plus 3 AB squared plus B cubed. Now we'll go ahead and let's use that. This gives us the limit as n goes to infinity. The sum, I goes from 1 to n, of 2 times 1, so this is 2, and then we have a 4i over n. Now we're going to subtract off 1 plus 2i over n cubed. Let's also write over here that a is equal to 1, and then our b is 2i over n. We have a cubed, so that's just 1 cubed, and that's 1. And then we have plus 3, a squared is 1, times b, which is 2i over n. And then we have 3 times a, which is 1. And then we have b squared, so this is 2i over n squared. And then we have b cubed, so this is 2i over n cubed. And all this gets multiplied by 2 over n. Now let's go ahead and multiply everything out. This is the limit, n goes to infinity. The sum, I goes from 1 to n. Let's see what we have. We have 2 plus 4i over n minus 1 minus 6i over n minus 3, and then 2i over n squared is 4i squared over n squared. And then we subtract 2 cubed, which is 8. So this is 8i cubed over n cubed, all times 2 over n. I think the biggest mistake I see students make, and sometimes I make too, is to not pull that negative through to all 4 of those terms. What we're going to do now is we're going to combine like terms. So we have our sum. Let's first combine our constants. We have 2 and minus 1, so that gives us a 1. And then let's combine our I terms. We have 4 minus 6, so this is minus 2i over n. Now let's look at our I squared terms. That is minus 12. So this is minus 12i squared over n squared. And then our last term is our I cubed term, and that's a minus 8. So we have minus 8i cubed all over n cubed times 2 over n. We are running out of space, so we're going to have to continue on to the next page. So let me just go ahead and let me grab this. And we'll put that on our next page. I went ahead and copied the formulas that we're going to need also, just to make it easier. What we need to do now is multiply all 4 of these terms by 2 over n. So we have the limit, n goes to infinity. The sum, I goes from 1 to n. The reason that we're multiplying through by 2 over n is we're eventually going to have to take the limit that involves n. So we need to have all the n's combined. This gives us 2 over n minus 4i over n squared minus 24i squared all over n cubed minus 16i cubed all over n to the 4th. Now we're going to use these formulas right up here at the top. So we're now going to have to distribute our sum to all four terms, and then we can use those formulas. This is equal to the limit as n goes to infinity. We'll put a bracket here because we're going to have four sums now. We have the sum, I goes from 1 to n, of 2 over n. And for these next three, I'm going to pull out the constant and the n power because the sum only involves I. So we have minus 4 over n squared. The sum, I goes from 1 to n of I, minus 24 over n cubed. The sum, I goes from 1 to n of I squared. And then our last one is minus 16 over n to the fourth. And we have the sum, I goes from 1 to n of I cubed. Now we can go ahead and use our formulas. We'll have to go up and down here. Let's look at this one first. 2 over n is a constant, so our sum is our constant times n. So this first piece is the limit, n goes to infinity, of 2 over n, that's our constant, times n. Now let's look at our next one. That is the sum of I. So this is minus 4 over n squared times n plus 1, all divided by 2. Then we have the sum of I squared. This gives us minus 24 over n cubed, n times n plus 1 times 2n plus 1, all divided by 6. And then our last one is minus 16 over n to the fourth. We have I cubed. There is our I cubed. So this is equal to n squared times n plus 1 squared, all divided by 2 squared, which is 4. Before we find the limit, we need to do a lot of algebra. This is what makes this problem difficult. Hang with me, we are getting close to being done. Limit as n goes to infinity. Our first term is 2 divided by n times n, so this is 2. And then our next term, that's this term right here. 4 divided by 2 is 2, so we have minus 2. Up top, we have n squared plus n. And then in our denominator, we have n squared. Now let's look at our third term. We have 24 divided by 6, so that gives us a minus 4. And now we have to multiply this out. N times 2n is 2n squared, and then we have another n, so this is 2n cubed. And then our outer term is n times n, which gives us an n squared. And then our inner terms are 1 times 2n, so that's 2n, and then we multiply by another n, so that's 2n squared. And then our last term is 1 times n, so that just gives us plus n. And all of this is divided by n cubed. And then we have one more term, and that's right here. This is minus 16 over 4, so this is minus 4. I'm going to divide the n squared on top into the n to the fourth on the bottom. So we just have an n squared on the bottom. And then we have to square n plus 1. So this is n squared plus 2n plus 1. Now let's see what we have. We have the limit as n goes to infinity. We have 2. Now let's look at this term. This gives us a minus 2 divided by n. Now we'll look at this term. This gives us a minus 8 minus 4 over n minus 8 over n. And then lastly, we have a minus 4 over n squared. And then we just have this last term. This is minus 4 minus 8n over n squared, so that's minus 8 over n. And then our last term is minus 4 over n squared. Before we take our limit, let's go ahead and let's combine these terms. Our 2 minus 2 cancels, so for our constants, we're just going to have a minus 8 and a minus 4. So this is minus 12. Now let's look at our terms divided by n. We have minus 2, minus 4, minus 8, and a minus 8. So let's see. That is minus 2 minus 4 is minus 6. And then we have a minus 16. So this is minus 22 over n. And then our last terms, we have a minus 4 over n squared and a minus 4 over n squared. So this is minus 8 over n squared. Now we're almost done. When we take the limit as n goes to infinity, this term is going to go to 0 because we have infinity in our denominator. And this term is also going to go to 0. So after all of this work, our answer is equal to minus 12. I think the key to doing this problem correctly is making sure that you double check your algebra as you go along. We're now going to work through 2 examples where we are going to evaluate a definite integral using geometry. A definite integral can sometimes be solved by interpreting it as an area or areas under a curve. In both of these examples, we are going to evaluate the integral by interpreting it in terms of areas. In our first example, we have the integral from 0 to 10 of the absolute value of x minus 5 dx. The absolute value of x minus 5 is the function that we're going to be integrating, and we're going to start by graphing this function. To make things easier, I'm going to write down the definition for the absolute value of x. It is a piecewise function, and it's equal to x when x is greater than or equal to 0, and then it's equal to minus x when x is less than 0. We can then write down that the absolute value of x minus 5 using the same pattern is x minus 5 when x is greater than or equal to 5, and then minus the quantity x minus 5 when x is less than 5. We are integrating our function from 0 to 10. So let's find out what our function is equal to at 0 and at 10. When x is equal to 0, the absolute value of x minus 5 is equal to the absolute value of minus 5, which is 5. And then when x is equal to 10, the absolute value of x minus 5 is just equal to 5. Let's also find what this function is equal to in the middle, where our function changes. So we get x minus 5 absolute value is just equal to 0. Now let's go over here to our graph and let's plot these points. When x is equal to 0, our function is equal to 5. And then when x is equal to 10, it's equal to 5. And when x is equal to 5, it's equal to 0. So our graph looks like this, which is what we would expect when we graph an absolute value function. Let's put here that this is 5, and then this is 10. Now we can interpret our integral as the area under these two triangles, this triangle and that triangle. So our area is 1/2 the base times the height for each triangle. We have 2 of them. So our area is 1/2 our first base, which is 5, times our height, which is 5. And then our next triangle is the same, 1/2 5 times 5. You can also think about putting these two triangles together, and then you would just have a rectangle with base 5 and height 5. This gives us an answer of 25. What we did was much easier than having to substitute our piecewise function in and integrate it. Let's now look at our second example. In this example, we are integrating from -5 to 0, and our function is 1 plus the square root of 25 minus x squared. We're going to start by breaking up this integral into two pieces because both of the functions that we are integrating have different areas. This is equal to the integral from -5 to 0 of 1 times dx plus the integral from -5 to 0 of the square root of 25 minus x squared dx. Let's start by looking at the integral from -5 to 0 of 1 times dx. Our function is equal to 1, so up here on our graph, I am going to draw the line y is equal to 1. And we're going to go from -5 to 0. Our height is equal to 1, and our width is equal to 5. So we can say that our integral is equal to our area, and that's our base times our height. Our base is 5, and our height is 1, so we get an answer of 5. Let's highlight this because that's part of our answer. Let's now look at our second integral. This one is definitely harder. We have the square root of 25 minus x squared dx. Our f of x is the square root of 25 minus x squared. And I think this is easier if we think about this as y. We can then square both sides and we get 25 minus x squared is equal to y squared. So we have 25 is equal to x squared plus y squared. So this is a circle with radius equal to 5. Notice now that we are integrating from -5 to 0. So we actually have 1/4 of a circle. And that circle looks like this, where this point is -5, and this point up here is 5, and that's 0. So we can say that our integral is our area, and it's 1/4 our area, which is pi r squared. So this is 1/4 times pi times 5 squared. And this gives us an answer of 25 over 4 times pi. Now all we have to do is add both of these up to get our final answer. So let's write down that our answer is going to be our first area, 5, plus our second area, which is 25 over 4 times pi. And there's our answer. Let's now learn about the comparison property for definite integrals and walk through some examples. The comparison property is a really useful property, and it's used to estimate the value of a definite integral by finding its upper and lower bound without solving it exactly. Let's say that we have a function y is equal to f of x, and we're going to estimate the value of the integral of this function from x is equal to a to x is equal to b. Capital M is the absolute maximum value of our function f of x between a and b, and then little m is the absolute minimum value of the function. Let's start by comparing the area under the curve y is equal to f of x to the area of our large rectangle that has a height of m and a width of b minus a. You can see from this graph that the area under the curve is less than or equal to this large rectangle. Now let's look at the graph right below it. Let's compare this area to the area of our small rectangle, which is little m times b minus a. you can see that the area under the curve is greater than or equal to this small rectangle. We can then put this all together and we can say that the integral from a to b of f of x dx is going to be greater than or equal to m times b minus a. That's our lower bound. And it's going to be less than or equal to capital M times b minus a, which is our upper bound. This is called the comparison property. Just to make things easier, I've written down some steps that we can follow when we use this comparison property to estimate the value of a definite integral. The first thing that we're going to do is calculate the derivative of what we're integrating and find the critical numbers. And then we're going to compute the value of our function at our critical numbers and at our endpoints and find the largest value and the smallest value. And then for step 3, we just use the comparison property to estimate the value of the integral. Let's now walk through some examples. We are going to walk through 2 examples where we are going to estimate the value of the integral that we're given using the comparison property. I've written the comparison property over here in this green box. Little m is the absolute minimum value of f of x on the interval, and then capital M is the maximum value of f of x on our interval. Let's begin by writing down that f of x is equal to x cubed, and our interval that we're integrating over is from 0 to 1. The first thing that we want to do is find the critical values of f of x. So we're going to take the derivative. F prime of x is equal to 3x squared. We set that equal to 0, and we get that x is equal to 0. That's a critical point, and it's also an endpoint. Our second step is to compare the value of our function at our endpoints and at our critical points. So we're going to compare f at 0, which is 0, to f at 1, which is 1 cubed, which is just 1. The smallest value is going to be little m, so 0 is little m, and then the biggest value is capital M. Now we can estimate the value of our integral using the comparison property. Little m is 0, so we have 0. We'll go ahead and put b minus a, but we really don't need to because we have a 0 there. That is less than or equal to the integral from 0 to 1, x cubed dx, less than or equal to capital M, which is 1, times b minus a, which is 1 minus 0. So we can say that 0 is less than or equal to our integral from 0 to 1, x cubed dx is less than or equal to 1. Our answer is then that this integral is greater than or equal to 0, but less than or equal to 1. Let's look at our second example. We are going to estimate the value of the integral from 0 to 2 of x times e to the minus x. We'll start by writing down that our function f of x is equal to x e to the minus x, and our interval is from 0 to 2. Our first step is to find the critical values, so we're going to take our derivative, f prime of x is equal to, we're going to need to use the product rule, so we have our first function x times the derivative of our second, which is minus e to the minus x, plus our second function e to the minus x times the derivative of x, which is 1. We set this equal to 0. Notice that we have an e to the minus x common to both terms. So we'll pull that out, and then we have a 1 minus x is equal to 0. An exponential function is never equal to 0. So all we're going to do is set 1 minus x equal to 0. And this gives us that x is equal to 1. And that's our critical value. Our second step is to compare the value of our function at our endpoints and at this critical value x is equal to 1. So we'll start with f at 0. This is 0 times e to the minus 0, so that's just 0. And then f at 1 is 1 times e to the minus 1. This is 1 over e. And this is approximately 0.37. And then f at 2 is 2 times e to the minus 2. And this is 2 over e squared, which is approximately 0.27. Now we want to compare all three of these values. Our smallest value is this value right here. So we're going to let this be equal to little m. And then our largest value is 1 over e. So this is equal to capital M. In our third step, we're going to substitute these values into the comparison property. Let's go ahead and write down our formula. We have little m times b minus a is less than or equal to the integral from 0 to 2 x e to the minus x dx, and this is less than or equal to capital M times b minus a. Little m is equal to 0, so we have 0 on the left-hand side, less than or equal to the integral from 0 to 2 x e to the minus x dx, less than or equal to capital M, which is 1 over e, I'm putting in the exact value there, times b minus a, which is 2 minus 0. So we can write down that our integral is between 0 and 2 divided by e. And that just gives us a nice estimate of our integral. And that's it. You've learned how to use Riemann sums to approximate the area under a curve, how the definite integral is defined as their limit, and how to apply the properties of definite integrals to evaluate and interpret them. You also saw how definite integrals can be used to find exact areas or estimate values using the comparison property. To really understand definite integrals, make sure to work through plenty of practice problems on your own. If this video has been helpful to you, please consider subscribing to my channel. Keep believing in yourself and have a great rest of your day.